Okay, hi. This lecture will introduce the Neyman-Pearson lemma, and I think, yeah, time for one example. And this is the second to last lecture for the course. Okay, so we have to start with a simple definition. Okay, simple definition too. A simple hypothesis is one for which the underlying distribution becomes fully specified under it, and a composite hypothesis is is not a simple one. Under losing my voice, a composite hypothesis, under it you don't fully specify the underlying distribution. So, I have what, 5 examples. Which ones are simple? This one is simple. We're assuming all the other, say there's only one, say theta is the only parameter. Then this is simple because now the underlying distribution is completely specified. What about this one? Not simple. What about this one? Not simple unless there's only two possibilities for theta 0. This one, not simple unless these are the only, well, still not simple, right? This one's definitely not composite. So this one's simple. This one, by the looks of it, is composite, right? Because you don't know if you're talking about theta 0 or something less than it. This is composite unless there's only 2. So unless only 2 possible values for theta. This one, composite by definition, right? You don't know which it is. This one, probably composite unless only 2. Okay, same, unless 2. Okay, that's the idea. So pretty straightforward. So, okay, so the next result, the Neyman-Pearson lemma, it's stated in a way so that both hypotheses are simple. But you'll see this is useful even in applications, even when that's not true. So far, all our examples in this chapter, we have not looked at one like this where both hypotheses are simple. There are real tests like this in applications, but as well, there's a way to extend this to all the tests, which is very nice, but it's stated this way. So we have the following theorem. This is called Neyman-Pearson, and let's give it. So when testing, so suppose we're testing for the test H0 versus HA Does that look like an A? There we go. Okay, HA, theta equals theta A. It still doesn't look like. The test that maximizes the power function, the probability of not making a type 2 error at theta A, is L, the likelihood, so this is the test, so this is the rejection region. Okay, so these are computable from a sample and from these, and we want to check that this ratio is less than some constant k, and where k is chosen based on alpha. Okay, so this is based on alpha. So really it's just saying it has this form, and then you find K based on alpha. So you can always find, for this kind of two simple hypothesis test, you can always find the best test in a sense, or a test that absolutely does the best it can at theta A, as we fix, as we set how well we want it to do under H0. All right, so I can make it so it only has a probability of making a mistake if theta equals theta 0. I can set that probability to alpha, and then I can guarantee myself that I get the best probability that I do reject if theta actually equals theta A. That's a great theorem, right? I like it. It tells you have the best test. Okay, so this is named after Carl Pearson and Jerzy Neyman. Pearson was British, I think, or Scottish, and Neyman is Polish, and Pearson had it first for sure. I think he was much earlier than Neyman, but this is called the Neyman-Pearson lemma. Okay. Well, let's do a little example. I actually fear this may be the one right from the book, but that's okay. That's okay. So to start, we'll just do an example that has this type of simple, two simple hypotheses. So suppose we have a single sample. That's a pretty small sample size, right? Doesn't have to be small or large, it can be any. So we have a single sample from the distribution f y given theta is equal to theta y theta minus 1. That's in the 0. And this is for, so in other words, y is, so in other words, if you remember, this means y is beta. And first parameter is theta, the second parameter is 1. Okay. Okay, so suppose we have a single sample from a beta theta 1 distribution, which has this PDF, and we want to test H0. The null hypothesis is theta equals 2, and the alternative is theta equals 1, and we want to do that at level alpha equals, say, 0.05. Okay, theta y to the theta minus 1 power, in here 0 else. Okay, so let's apply the theorem, the lemma. So the question is find test that maximizes the power function at theta equals 1. We have to compute the likelihoods. So I have Ly1. The alternative hypothesis, if I plug in 1 for theta, I just get the uniform distribution, right? Actually, beta 1, 1 is uniform. So, so this is just equal to the uniform. This is just equal to 1 if y is between 0 and 1. What about Ly2? Ly2, I plug in 2 for theta, I get 2y. So this is just equal to 2y times 1, 0y. So the lemma says, so we know we have Ly2 over L1 less than k is the best test. So we have 2y less than k. This is the rejection region. Is most powerful at theta equals 1. K will be set by alpha completely. It's set by alpha being 0.05. So for simplicity, we could first change K to call it something else. So this is equivalent to, just to make it a little less cluttered, to simply y less than k. If you want, call it k star or something like this, but you could just call it k again. Okay, and to set k star now, we require 0.05 equal to the probability y is less than k, given theta equals 2. But that's just equal to 0 to k, or k star, maybe be picky about it, dy, so I get k star squared. Okay? And I want that to be 0.05, so k star is just equal to the square root 0.05, which is equal to 0.224, and the test RR y less than 0.224 is most powerful among, so that's the language, you say powerful, most powerful among all 0.05 level tests. Okay, well, this is pretty restrictive for only the 2 simple hypotheses cases, so we want to see how we can extend it to composite hypothesis. We'll do that in the next and last lecture of the course. You've made it. One more to go. So take care, stay safe, and click on the next lecture.